Friends, let me show you some pictures of mathematicians here. All of these are the mathematicians who have made significant contributions to the development of the mathematics we use today. For example, Srinivasa Ramanujan, Isaac Newton, Archimedes, Pythagoras, Aryabhata, Euler, Brahmagupta, Hilbert, Riemann, and along with them, many other mathematicians are also included in this list. But today, I want to introduce you to a mathematician from the 17th century named Pierre de Fermat, who is known worldwide because of his theorems, such as Fermat's Last Theorem, his Little Theorem, Fermat numbers, and the Fermat principle. He is also considered the founder of the modern theory of numbers. He contributed to differential and integral calculus, number theory, optics and physics, and analytic geometry as well. However, he was not a mathematician by profession, rather, he was a lawyer. But the work he did in mathematics and physics makes him a very famous mathematician. Out of his many works, the one we are interested in today is the last theorem he proposed. The one we are interested in today is Fermat's Last Theorem. Many of you had requested a video on this topic. So today we will learn about Fermat's Last Theorem in complete detail. Along with that, we will also find out how this theorem was proved and by whom. So, without wasting any time, let's start the video. Now, if you are a mathematician, you would be well aware of Fermat's last theorem, but if you are a student, then probably you haven't studied this theorem. So instead of directly learning its statement, we will first understand the concept behind this theorem, what exactly it is trying to tell us. So first of all, let me introduce you to the number line. So look at the screen, this is our real number line, and at its center is the number 0. On its left-hand side are all the negative numbers, which go up to minus infinity, and on the right-hand side of this number line are all the positive numbers, which extend up to plus infinity. So the most important thing here is that Fermat's last theorem only works with positive numbers. It only covers the right-hand side portion of the number line. For example, 2, 3, 4, 5, and so on till infinity. Now to make this even simpler, instead of calling them positive integers, we'll just call them simple numbers. So now I'll show you a very simple equation. Look at your screen, here is that equation. A plus B equals C. This is a very basic and very simple equation. This tells us that if you add A and B, you will get the number C, or the number C is equal to the sum of A and B. Now here you tell me some values which will satisfy this equation. I know. You can give a lot of values for this. For example, if you put the value of A as 1, the value of B as 2, and the value of C as 3, then this equation will be satisfied because a plus B will be proven equal to C. 1 plus 2 equals 3, and on the right-hand side as well, the number is 3. So, the left-hand side and the right-hand side are both equal, and this equation is verified. In the same way, you can put 3 in place of A, 5 in place of B, and 8 in place of C. Then in this case as well, our equation will be satisfied. This is quite a simple case because here you can assume infinite values for A, B, and C to satisfy this equation. That means we can all easily accept that this equation can have an infinite number of solutions. If you don't believe it, then you can try it out yourself practically. Now that was quite a simple case. Now let's take the difficulty up another level. Now here, I'll show you another equation, so look carefully at this equation on your screen. A squared plus b squared equals c squared. We've squared all the terms a, b, and c. Here, the sum of a squared and b squared is equal to c squared. Now in this too, I'll ask about some numbers that satisfy this equation. Now you also tell me some values that satisfy this equation. And I know, looking at this equation, a triangle must have formed in your mind where A is the base of the triangle, B is the perpendicular, and C is the hypotenuse. So seeing this equation must have definitely reminded you of a triangle. An image of the Pythagoras theorem must have formed in your brain, and you definitely know some values that satisfy this equation. For example, if you put 3 in place of A, 4 in place of B, and 5 in place of C, then in this case, the equation will be satisfied. Similarly, if you put 6 in place of A, 8 in place of B, and 10 in place of C, then, in this case as well, the equation will be satisfied, and if you have studied geometry well, you must already know about many Pythagorean triples. For example, if you put 5 in place of A, 12 in place of B, and 13 in place of C, then again this equation will be satisfied because 5 squared is 25. 12 squared is 144 and 13 squared is 169. So 25 plus 144 equals 169. That means this equation is satisfied. Now, if you search for a list of Pythagorean triples on Google, you'll find many such numbers that satisfy the equation a squared plus b squared equals c squared. In fact, not just many numbers, but you'll actually find infinite answers in this. That is our earlier equation a plus b equals c, and the second equation a squared plus b squared equals c. In this case, there can be infinite numbers of solutions that will satisfy these equations. At this point, you must be finding this game of satisfying the equation quite fun and amazing. So now, let's continue this game further. So now, after looking at the second equation, I'm going to present a third equation to you. And I know many people might have already guessed what this equation is going to be. So here is that equation. You guessed it absolutely right. A cubed plus b cubed equals c cubed. Now you have to do the same thing that you did in the case of the previous two equations. You have to find such values that satisfy this equation. So put some thought into this and try to think of 3 values for a, b, and c that will satisfy a cubed plus b cubed equals c cubed. At first glance, this equation seems quite simple to us, but I know that none of you were able to find its values. No one has been able to find 3 such values of a, b, and c that satisfy a cubed plus b cubed equals c cubed. Even if you use a calculator or even a computer, it won't help. No matter how much time you take, you still won't be able to find any values that satisfy a cubed plus b cubed equals c cubed. Maybe there's a problem with this third equation, so let me show you a fourth equation, and that equation is a to the power of 4 plus b to the power of 4 equals c to the power of 4. Now try to find values that satisfy this equation. If you also fail to satisfy this one, then it's nothing new for mathematicians. Try to satisfy yet another equation. A to the power of 5 plus b to the power of 5 equals c to the power of 5, and I can bet you won't be able to satisfy this equation either. You satisfied the first and second equations quite easily, but when we moved on from the third equation, this equation, which seemed quite simple, became much more difficult. For the third, fourth, fifth, and all the other upcoming equations like these, you will find that there are no positive integers that satisfy these equations. And in the 17th century, Fermat stated this very thing in his last theorem. So, the statement of Fermat's last theorem tells us that no integers a, b, and c can satisfy the equation a to the power n plus b to the power n equals c to the power n. When the value of n is greater than 2, that means no 3 positive integers a, b, and c can satisfy the equation a to the power n plus b to the power n equals c to the power n. When the value of n is greater than 2, and this is Fermat's last theorem. And you all just saw this being proved earlier. Here, we considered a total of 5 equations. In our first and second equations, we were able to satisfy the equation with infinitely many integer values. But as soon as we reached equation number 3, we found that no matter how much we think or how hard we try, we still won't be able to find any 3 integers that satisfy this equation. Not only that, we saw the same thing in the case of the fourth and fifth equations as well. And if you keep extending this equation up to any number n, that is a to the power n plus b to the power n equals c to the power n, then you will also find that for cases where n is greater than 2, there is no solution here either. So look at the beauty of this theorem. For n equals 2, there are an infinite number of solutions here, but for values greater than 2, there are infinite cases, yet not a single one of those infinite cases has a solution. This is the beauty of Fermat's last theorem. Fermat believed that he had an amazing and wonderful proof for this statement and theorem, but the proof was so large that the size of his book was quite small in comparison to it. In fact, there wasn't enough margin in his book for him to write the proof of this theorem, which is why he never actually wrote down the proof for his theorem. But in 1995, after remaining unproven for several hundred years, this theorem was finally proven by Andrew Wiles. How Andrew Wiles managed to prove it is a separate story altogether, which we will learn about in another video someday. But let me briefly explain to you how he proved it. So Fermat's last theorem was proven using contradiction. If this theorem is false, then it would be possible to construct an unusual elliptic curve, and this unusual elliptic curve is called the Frey curve. Meaning, if Fermat's last theorem is false, then you can construct this Frey curve. And if you cannot construct this Frey curve, then Fermat's last theorem is true. So, this is an example of proof by contradiction, and Andrew Wiles proved that Frey curves do not exist in this world. So indirectly, what does this mean? That Fermat's last theorem is true. Anyway, the full details behind its proof are a whole different story, which we will discuss in another video some other time. So, tell me how you liked this video. I hope you really enjoyed it. If that's the case, please like this video, share it with your friends, and if you haven't subscribed to our channel yet, then do subscribe so you don't miss any future videos or updates.